So, Lecture 4 in our 7th learning unit, Chapter 19 on complex ionic equilibria, actually has us reconciling a lie we sort of told you in Gen Chem 1. So, we're going to be dealing with the solubility of ionic compounds. And as I'll highlight in the beginning part here, in Chapter 4 in Gen Chem 1, we discussed the concept of certain salts being soluble or insoluble. And so what we'll reconcile now is that no salt is truly absolutely insoluble. It has what we call sparing solubility. And so a little bit will dissociate into its component ions, and that is dependent on an equilibrium constant that we call KSP. So remember, all of our equilibrium constants are big letter Ks, and we can indicate kind of what kind of an equilibrium constant is by the subscripts found after. So for example, we had Kcs and Kps from chapter 17. In chapter 18, we learned about Kas and Kbs and Kws, and now we learn about Ksps. And this has to do with solubility. So SP actually stands for solubility product. So a lot of what we've already learned about equilibria is going to apply here. So we're going to use the same rules for writing equilibrium constants. We're going to be solving type 1 and type 2 type equilibrium problems. Again, type 1 being ones where we're actually going to solve for K. Type 2 problems where we're going to be using a K to solve for equilibrium concentrations. And so a few homework problems that'll allow you to practice that, but we're going to go through some of these basic skills in today's lecture. So again, the first thing is to tell you guys that, you know what, we actually lied to you a little bit back in chapter 4 in Gen Chem 1. Maybe you remember this table. This was a table that I told you that you didn't need to know for Gen Chem 1. We provided it for you, but you used that to determine whether or not precipitates would form if you mixed two solutions together. So for example here, you learned last semester looking at solubility that all common fluorides were soluble except lead and anything from group 2A. So you would have said that lead fluoride was insoluble. However, one of the things that we'll realize in this chapter is it's sparingly soluble. So again, this solubility is not a black and white issue. It's not that it's completely soluble or it's completely not, as this table would lead us to believe. Rather, this is mostly insoluble, but a few ions are able to escape into the aqueous kind of solvated state. So some of the things to think about in our first sample problem is actually going to stress this is how we write KSP values. So for any ionic compound here that has some type of a metal and then some type of an anionic species, we can write KSP like this. And so let's elaborate just a little bit more so we can make sense out of this equation, right? If we have some metal that's M sub P times X sub Q, we can write solubility so that this is going to be M to the N plus whatever that charge is on that ion, and then we can write a coefficient in front of that as P, and then X to the some type of, that's not necessarily a 2 there, that's a Z there to indicate that there's some charge on our anion. And then again, we're going to have Q as a coefficient. So again, if we put the fact that we start with a solid and we end up with aqueous ions, if we were to write an equilibrium expression, remember that we exclude pure solids from our equilibria expressions. So even though we normally would write products over reactants, in this case, the reactants are solid, so they would not appear in an equilibrium expression. So KSP really appears as just the product of the two ionic species raised to powers that are coefficients from their dissociation. So our next sample problem is actually going to give us an opportunity to practice that. But a couple of things to sort of think about are ways that solubility might be affected by things that we've already learned about, sort of acid-base chemistry. So sort of one that you want to sort of keep in the forefront of your mind as we discuss things here are anything that's a metal sulfide. So that's going to be a metal that's bound with the S2- ion. Because the S2- is a fairly basic molecule, if there's any S2- that we have in solution, it will find water, and this actually should be a one-way arrow here. It's going to find water, and it's going to take a proton from water, leaving behind hydroxide, and generating what is the conjugate acid of S2-, which is HS-. And again, this is going to be a one-way arrow that allows us to make our solution fairly basic. So for any metal sulfide, and looking here at the example of manganese sulfide, if we take that metal sulfide and we dissolve it in water, the equilibrium really is going to look like this. We generate the metal cation, and then we don't generate S2-, we actually have HS and OH-. S2- is such a strong base that we really don't have any of it live in that form. It really lives in these forms, which is why those are what appear in our equilibrium expression there. So those are the species that are represented here. So again, just to highlight here, we are not going to see S2-. S2-, if it's in solution, really appears as HS- and then hydroxide. So just one of those little things you want to make sure to keep in mind. If you see a metal sulfide, this is what your KSP is going to look like. Okay, so an opportunity for you guys to practice 4 problems that we have here. So I'll kind of reveal them one at a time so you can have an opportunity to practice writing and then seeing what the solution is. So go ahead in a moment and pause the video and try to work out writing an ion product expression. So that's writing the KSP for magnesium carbonate. As a hint here, start by writing what the chemical formula is for this. Yeah, all that stuff from Gen Chem 1, learning how to name things and take a name and make a chemical formula from it, still very important, especially now at this point in this chapter. So write magnesium carbonate as a chemical formula, and then show what you get when it dissociates in water. Once you have that balanced equilibrium equation, then you can write your KSP. So pause the video and go ahead and try and do that for magnesium carbonate. So again, magnesium carbonate is MgCO3 solid, dissociates into a divalent magnesium cation, and then carbonate, CO3, which is 2-. Writing a KSP, because we don't have solids appear in our KSP expressions, and there's no coefficients here that we need to worry about. The solubility product, the KSP, is just the concentration of magnesium times the concentration of carbonate. Okay, another one to try. Try iron 2 hydroxide. Pause the video and try for yourself. So iron 2 hydroxide, again, building what this formula looks like. Iron 2 is going to be iron 2 plus. Hydroxide is OH-, and so this is what the chemical formula will look like for iron 2 hydroxide, FeOH2. So again, this is going to generate 1 divalent iron cation in solution, and then 2 hydroxide ions in solution. So the KSP is going to look like this: the iron concentration times the hydroxide concentration squared. And it's important to note here, we've spent a lot of time over the past 2 chapters looking at acid-base chemistry, which was largely just looking at coefficients that were 1s. So we have to make sure we remember here, coefficients that are going to be part of our balanced chemical equation are going to become exponents in our equilibrium expressions. So make sure that we don't forget those. All right, calcium phosphate. Try writing a balanced chemical equation for its dissociation and then the corresponding KSP. This one reminds us that if we're building a formula unit, an ionic compounds formula, we have to make sure that we sort of have this cross multiplication in terms of figuring out sort of the simplest whole number units that we have for these to generate a formula unit. So calcium phosphate is going to be Ca3PO4, again, the quantity 2. And so when this dissociates, we actually get 3 calcium ions and 2 phosphate anions. And again, this is a polyatomic anion that we have there. So the KSP here is the calcium ion concentration cubed times the phosphate concentration squared. So one of the things that we will start to see in these problems is we're going to have coefficients that get to be fairly large numbers. That's going to make for some really unique algebra when we do type 2 type problems where we might have to take, something to the 1/5 power. So again, we'll deal with those problems towards the end of this lecture. Go ahead and try silver sulfide. And again, highlighting when we have that sulfide, remember what we have to think about in terms of the balanced chemical equation for its dissociation. So again, silver sulfide is going to be silver as a cation, a monovalent cation, and then sulfide is S2-. So this is what this guy looks like as a balanced chemical or a formula unit. When it dissociates, it will generate 2 silver cations, and while it does generate sulfide, remember from our previous slide here, sulfide is not going to live in water. It's going to find a water molecule, strip a proton off to generate HS-, and leave behind hydroxide. So these 3 species are really what's going to be present as ions in solution. So those are the species that we see in our KSP expression. So moving on to sort of the second half of this lecture is really dealing with how we solve type 1 and type 2 problems when we're dealing with solubility. So I want us to still keep thinking about and using the same strategies that we've thought about for these problems. We're going to write a balanced chemical equation. We're going to write an equilibrium expression. We're going to make sure that everything's in the right units. We're going to set up an ice table. We're going to solve for X. So a lot of this is going to be similar to things that we've seen before. Again, what's just going to be different is the chemical equation that we're using to think about equilibria. So just to highlight a couple of hints and tips here that are kind of important and unique to this kind of a problem. When the problem is asking about solubility, what they're really asking for is what is X? What is the value of X from an ice table? So knowing that, if they tell us the solubility in water, think about how that could help us solve this problem. To give you the answer ahead of time, if you'd like to work through it on your own, the KSP value is going to be equal to 1.96 times 10 to the minus 8th. So take a minute and try to work through this problem on your own, or let the video play for the worked out solution. So we're going to always start these problems the same way we always did. Start with a balanced chemical equation for the chemistry that's going on, in this case the dissociation of a sparingly soluble salt into its component ions. Write an equilibrium expression. So KSP is going to be equal to the concentration of lead times the concentration of sulfate, and for this problem we want to calculate what that value is. Now, one of the things that we'll see in these kinds of problems is that we might see units that are different from our traditional molarity, and that's okay for these problems that we'll see. For this problem, though, again, we're going to start with no ions from any other solutions initially. So we're asking how much are we making of these? So this is really a plus X and a plus X. So X is going to be equal to the equilibrium concentrations of each of these, and X is really also equal to the amount of lead sulfate that has dissociated. So again, when they ask for the solubility, they're really asking for what is X. And so again, we need to use this information where they tell us the solubility, so it's really telling us what X is. So see if you can finish working through this problem now that we know what the value of X is. Again, telling us what the solubility of lead is really is telling us what X is. So again, with this problem, they give us the units in something different from molarity, but because we know we need to have molarity in order to use and think about an ice table, we need to do some calculations in order to convert this into molarity. So again, some basic unit conversions. We're going to have a prefix unit conversion to convert to liters. And then we need to use the molecular weight here in order to convert into moles. Doing so gives us the concentration of lead, or the solubility in lead of water, as 1.4 times 10 to the minus fourth molar. That's equal to each of these concentrations at equilibrium. And so we're really then just multiplying these two values together to get the KSP value. So one of the things that we need to make sure that we are very cognizant of as we're doing these kinds of problems is that it's very common to see coefficients that are not equal to 1. So again, some of these that we see up here, there might be two ions that are produced, but again, the anion to cation ratio is 1 to 1, so those coefficients will be 1, and so we don't really need to worry about those there. But we're going to see a lot of salts here that are going to have non-1 coefficients. Make sure that we don't forget these in our ICE table, and our next problem is going to allow us to practice that. So, and I've drawn just a little picture here to help us think about this next problem. But again, this is another determining KSP problem, so a type 1 type problem. So we're going to see a lot of problems here that talk about either forming precipitates or solubilizing something. So again, this problem tells us when lead fluoride is shaken with pure water at 25 degrees C, the solubility is found to be this number. This is kind of related to what the previous problem was telling us, that they're telling us what X is. But this is really sort of what's going on here. You're going to take a large chunk of this lead fluoride and you're going to put it in some water. You're going to shake it up, do all kinds of things. You're going to wait for that solution to reach equilibrium, and some of that lead fluoride is going to go into solution. What you then do is you look at the amount of lead that you have in solution. And again, if we write a balanced chemical equation, we're going to see that that would be equal to X. So once we know the solubility of lead here from this, and we know that that's X, we can do just like we did in our previous problem, and we can calculate what the KSP value is going to be. The KSP for this problem is 7.0 times 10 to the minus 8th. So I encourage you, try to pause the video right now and see if you can work through this problem the same way we worked through sample problem 19.6a, and see if you can arrive at the correct KSP value. So thinking about what's happening here, again, treat these problems all the same. Start with a balanced chemical equation, noting that this time we are going to have a coefficient that is not equal to 1. Write your KSP expression, making sure to include that non-1 coefficient as an exponent. And understanding now that we're going to multiply the values that we get for these equilibrium concentrations times each other with the fluoride concentration squared, and that will give us our answer, our KSP value for lead fluoride. So again, nothing is relevant with our solid in our equilibrium expression. We start out with no lead or fluoride from any other sources, and we're going to make X amount of lead and 2X amount of fluoride. Again, they tell us the solubility is found to be 0.64 grams per liter, so they're basically telling us what X is. So again, that tells us what X is there. So if you were stuck getting this problem started, now that you know a little bit more, try to finish it out. So again, just like we saw with our last problem, they give us the solubility of lead, but they give it to us in units that are not molarity. So we need to do a little bit of work to convert 0.64 grams of lead fluoride per liter into a molarity. So again, we can use the molecular weight for that. No need for a prefix conversion. We're already in units of liter. And so we get that the solubility, now we'd call molar solubility, is 2.6 times 10 to the minus third moles per liter. So that's equal to X. So we know that that is going to be the concentration then of lead at equilibrium. But just kind of looking at this unit conversion down here, this helps us again understand that we've got sort of a molar ratio that we need to have that allows us to have twice as many fluoride as we do lead. And so this needs to be multiplied by 2. And ran out of room here to finish out this problem. But again, this concentration is going to be equal to 2.6 times 10 to the minus third. I have to double it to get the fluoride concentration. And then to figure out my KSP, I actually have to square it. So if this problem was just asking for maybe the fluoride concentration, it would just be double this value. And again, doubling that value in either units. But to get our KSP, we need to put the lead concentration in, 2.6 times 10 to the minus third. This number is doubled to get the 5.2 times 10 to the minus third, but then we also have to square that for our KSP. So that's how we get our 7.0 times 10 to the minus 8th. All right, moving on to a few type 2 problems. So calcium hydroxide, another one of these species that's sparingly soluble. Again, a little bit of a backstory here. It's a major component of mortar, plaster, and cement, and solutions of calcium hydroxide are used in industry as a strong and inexpensive base. Okay, so it says calculate the molar solubility. This is just another one of those clues. If something says, what is the molar solubility? They're basically asking you, what is X? So again, calculating the molar solubility of calcium hydroxide in water, they give us the KSP, so this becomes a very typical kind of problem that we'd see previously. So kind of giving you the answer here so that you can try to work through it on your own. The molar solubility here is going to be 1.2 times 10 to the minus second molar. So that's the answer you should be getting. So pause the video and see if you can work through this problem on your own. Again, if you're getting stuck knowing where to start, always start out the same way. Write a balanced chemical equation for what's going on. Write an equilibrium expression. And again, this time they gave us the value of KSP because we want to solve for equilibrium concentrations. Set up your ice table. Again, we're only going to have products appearing in our ice table. So this is going to be plus X plus 2X. Remember, those coefficients matter here. So X and then 2X. Now this is another point we have to make sure that we don't lose some important information. The KSP value is going to be equal to X times the quantity 2X squared. Make sure that you just don't write 2X and then the squared by the X. That 2 applies to both of these species. So this ends up being the quantity 4X cubed equals our KSP value. Okay, so a classic place that students make mistakes is not making sure to either include that exponent or to distribute that exponent to both the coefficient and the variable. Okay, so having 4x cubed equal to this, little bit of algebra that we probably haven't seen yet, we're going to divide both sides by 4 to isolate the variable by itself, and then we need to take the cube root. So make sure that you know how to do both of those in your calculator. Solve for x, which is 1.2 times 10 to the minus second, and remember, solving for x is solving for the molar solubility of calcium hydroxide. So just a little heads up, another way that you might see this problem is you might be asked, what's the pH of this solution, right? So if we think about that, then we'd need to solve for this concentration. It's going to be double what X is. So 2 times this value will be the hydroxide concentration, and doing our around the block could figure out what the pH is based on that hydroxide concentration. Okay, a little bit more background before we move into our last couple of problems here. Something that we've actually seen already, but I haven't really defined it yet for you, is something that's called the common ion effect. So when we have an ion that's added to an equilibrium mixture that already has that ion, the position of the equilibrium will shift away from it. So that's kind of a little bit of some scientific jargon, but we saw that at the beginning of this learning unit when we talked about acidity. So for example, if we have a buffer solution that has a weak acid and its conjugate base, this weak acid is not going to dissociate as much because some of the bucket is already filled with the conjugate base here. So we can think about this from sort of an equilibrium standpoint as well. We're not going to be able to slide as much of our weak acid over to the other side, making the conjugate base and H+, if we've already filled up that bucket a little bit by a conjugate base that's already been added. So again, we call this the common ion effect. We saw it with acidity in the beginning of this learning unit, and we saw it again when we had a buffer solution. And what we're going to see now is we're going to see it with regards to solubility. So in this first section, we're going to decrease the acidity of molecules by filling up the product side with a common ion. And we're also going to see a decrease in solubility if we fill up the right-hand side with a common ion. Okay? And again, this is a way of also thinking about Le Chatelier's effect. Remember, that was sort of our push and pull to be able to think about equilibria. So if we're going to add a reagent, that pushes the equilibria to the other side. So if we're adding extra amounts of something that's on the right side of an equilibrium, it's going to shift that equilibrium to the left. It's going to make this species less acidic. It's going to make this species less soluble. So again, we can think about this qualitatively and we can think about it quantitatively. So you might see a question on part 1 of the exam that asks how the solubility or the acidity will be affected when you add a specific common ion. And what we're going to do now is actually do the quantitative piece of it and actually see it played out with some numbers. Okay, so this is just another example of thinking about that push-pull. When we think about how pH might affect solubility, and maybe you already know this, if you were to put a piece of chalk in an acidic solution, it would actually bubble and it would dissolve the chalk. And that's different from putting the chalk in water. Okay, this could be chalk as calcium carbonate, or it actually could be limestone. Okay, but we can actually see that played out with equilibria here. So if we take the first part here and imagine taking a piece of calcium carbonate, and whether you think of that as being chalk, whether you think about it being limestone, sparing solubility, so we have a little bit of calcium ions and then a little bit of carbonate ions that we'd have as that salt dissociates. If we acidify the solution, if we decrease the pH, if we add more acid to solution, what's going to happen is that acid is going to react with this conjugate base and it's going to generate the conjugate acid. What's really happening is we're pulling this guy out of solution, which means this equilibrium is going to shift to the right, which means we're increasing the solubility of this. Well, you may or may not remember from Gen Chem 1, this is actually something that we talked about. When we have HCO3 in solution and we further acidify it, we actually make H2CO3. And H2CO3 is carbonic acid, which can readily be converted into carbon dioxide and water. Okay, so this is, again, one of those unique things that I want you to be able to think about. So like we had sulfides when we had S2-, if you've got carbonate salts, okay, what can happen is as you acidify the solution, as you add acid, it's going to increase the solubility of this because it pulls this whole equilibrium to the right. And it's also going to be generating some bubbles because it's going to be making carbon dioxide gas. So kind of another unique, specific sort of solubility situation. So our next sample problem is going to actually build on a sample problem that we've done already. In sample problem 19.7, we calculated the solubility of calcium hydroxide in water. So basically asking if there's nothing else in that water and calcium hydroxide is allowed to dissociate to whatever extent it's going to, what's the solubility of that going to be? So we build on this and we say, well, you know what if we added 0.1 molar calcium nitrate to solution? Again, if we've added calcium nitrate, We have to remember and think about the fact that that's going to be adding calcium ions to solution and nitrate ions to solution. Well, nitrate ions are going to be spectators, so that's not anything I need to worry about. But if I'm adding extra calcium ions already there, if I'm filling up that bucket already, if you will, with calcium ions, hopefully based on our previous discussion, you should be thinking that the solubility of calcium hydroxide is actually going to go down if we've got a common ion that's there. The question is, though, how much? So remember, when we have a problem that says, what is the solubility? That's really asking us, what is X in our ice table? So knowing those few pieces of information, see if you can work through this problem and get that X, or the solubility, is going to be equal to 4.0 times 10 to the minus third. So go ahead and pause the video and see if you can work through this modified version of sample problem 19.7 now when we've added a common ion. So treat all these problems the same. So again, we're going to have an equilibrium here that allows calcium hydroxide to dissociate into calcium ions and then hydroxide ions. What is different now is we are already filling up our cup of calcium ions by adding calcium nitrate. And because calcium nitrate is completely soluble, this is a one-way arrow, the concentration of 0.1 molar calcium nitrate means we've also got 0.1 molar calcium ions. So that's where that piece comes from. No other sources of hydroxide. Then our ice table continues in our change column like we'd expect. We've got plus X and then plus 2X. So now this is going to be 0.1 plus X and then 2X. So now that we know what these values are, and again, they give us the KSP, how do we go ahead and solve for X there? So what we're going to see here is we're going to do the same type of things that we did in previous problems where we wanted to simplify our algebra. So again, we've got 0.1 plus X and then the quantity 2X squared. That's going to be equal to 6.5 times 10 to the minus 6th. Now, if we had to go through and kind of factor all of this in, my goodness, we would have, some complex algebra. So let's see if we can make a simplifying assumption that X is going to be small. If X is going to be small, 0.1 plus X simplifies to 0.1, and now all of a sudden this again becomes manageable algebra. Go through and solve when we get that X is equal to 4 times 10 to the minus third. I just want to flip back for a second and highlight 4 times 10 to the minus third. If we flip back here, 1.2 times 10 to the minus second. We got a smaller number, which is what we predicted. We predicted that the solubility would go down, and that is absolutely what happened here. Solubility went down. The rest of this problem just kind of goes through and says, you know what if we wanted to actually calculate what those solubilities were? Okay, that we would just put those values of X in to calculate what the calcium and then hydroxide concentrations were. This is just a little note. If you happen to watch the video that's online for this, I believe there's a slight error on the video in terms of just reporting what this number is, but everything else is totally fine with that. But again, this could be a problem where I could ask you, what's the pH of this solution? And if that's the case, you'd have to take this hydroxide ion concentration and use that to determine pH. So last problem here, and I really should say that this is a qualitative problem. We're just asking the question whether or not addition of a strong acid is going to affect the solubility of this compound. So again, in order to think about that, we have to think about if chemistry would happen if we were to add hydronium ions. So that's sort of the big question. Thinking about if we were to add hydronium ion, do we have any ions that are in here that would want to do acid-base chemistry? So think about that and try to work through this first problem here. So again, think about adding hydronium ion. Do we have any potential for chemistry? So again, thinking about what we have here with lead bromide, we're going to have a little bit of lead ions and bromide ions in solution. Neither of those are going to want to do chemistry with H+. Remember, we're not going to have chemistry happen with lead 2+ because we'd never have two cations do chemistry with one another. So the question really is do we have any chemistry happening between these two? Well, because we know that HBr is a strong acid, there's not going to be any effect that we're going to see there. Okay, try the next problem, copper 2 hydroxide. If we're going to be adding H+, are we going to have any additional chemistry that pulls this equilibrium forward? So copper hydroxide again would dissociate into copper ions and hydroxide ions. Well, H+ certainly is going to want to do some chemistry with OH-. It's going to want to generate water. So in doing so, we would pull this hydroxide out of the solution. That's going to be a pull on our equilibrium, which shifts the equilibrium to the right. Shifting the equilibrium to the right with this kind of an equilibrium means we increase the solubility of copper hydroxide. All right, last problem here. Again, you think about working through this problem. Iron 2 sulfide. Thinking about iron sulfide, again, remember that's going to break up into Fe2+ and S2-. And even if there was just water around, even if it wasn't an acid, it would allow us to shift this equilibrium, generating HS-. And again, that's going to pull this equilibrium to the right. We are going to increase the solubility of iron sulfide. So these problems, just as a side note, all had to do with the addition of hydronium ion, addition of acid. We could have easily seen these same three species and asked the question about adding something like copper nitrate to solution. That would actually decrease the solubility of this one and would have no effect on the other two. Another example that wasn't part of this kind of series of problems here was what if you were to have, again, a carbonate salt? So for example, like copper carbonate. What if you were to have copper carbonate and you added a strong acid to that? Again, that would pull that equilibrium forward for the same reasons that we see these guys interacting with H+, we'd see CO3 2-, which is again a base. It's the conjugate base of a weak acid wanting to do chemistry with H+. All right, so that wraps up our lecture on salt solubility. So again, be able to write a chemical equation for the dissociation or the partial dissociation and equilibrium of a salt. You know, KSPs are what we're going to represent there. And again, think about doing both type 1 and type 2 problems. Make sure to watch your coefficients. And again, qualitatively, think about how we might add ions, right? We can have common ion effects. We can have reactive ion effects. And again, we can think about those as either increasing or decreasing solubility of salts.